DNS takes a domain name and it translates it into an IP address. We're going to create our own DNS client from scratch by coding the entire protocol stack from Ethernet and down to DNS. Let's get going. What's up guys, welcome to today's show. So today we're going to create a DNS client, and DNS works like this. If you go to some link like www.google.se, you need to translate this into some IP address before you can send any packets to it. And if you run the command nslookup and then this thing, we can see that this domain name is actually this IP address. First, we send a request to the root DNS servers, which are responsible for the whole of the internet. It's going to be redirected to a set of servers that is in charge of this so-called top-level domain, the .se, and it's going to be redirected to Google's DNS servers, and they will have the IP address in their database for this domain name. First, we need Ethernet in order to be able to send it on the local network. Then we need IP to send it over internet. We're going to need UDP, which is used to differentiate between different services like DNS or HTTP, etc. Actually, HTTP was a bad example, but DNS is correct. And then we have DNS. So we need to create a struct star or something. So these protocols in order. And I'm gonna make this a little bit simple. I'm gonna keep everything in one struct. So as of now, I have only created a default makefile which compiles the C file, and I have created a simple.h which has some includes and some integer types and some macros for converting between the types, typecasting. All right, so let's define this struct, and the whole struct will work the same way at each level. So we are going to create a struct. Let's call this packet. So it's going to be a struct of structs basically. So we're going to have an anonymous struct, which is going to be our Ethernet. And then we're going to have another anonymous struct, which is going to be IP, and so on and so forth. And in order to be able to know what we're going to put in here, I'm going to use Wikipedia, which is kind of good for this purpose, I think. So what we do is we search for Ethernet packet wiki. We go to this Ethernet frame, and what we are interested in is the different fields. Let's see. All right, so this is all we need. Destination MAC address, which is just 6 8-bit integers in a row. And then we have the source MAC address. And then we have a 16-bit type field, which tells the operating system what the next protocol in the stack is. So our ether type will point towards IP in this case. So let's create something like this. So we need to have sorry, we need to have an array of integers. So let's call this, let's just call it a destination. And we're gonna need 6 of those. And same with the source. And then an int16 for the type, like this. And this is the whole Ethernet part of this. So I'm going to call this E, like this. All right? So this is the first part of it. And then we go to IP, and we want the Internet Protocol. And this is a little bit more involved. Let's see. IP packet. Here we go. IPv4 packet. Because there are 2 different versions, but we are going to focus on the classical one, the IPv4, which is still in use. So as we can see here, we first have a version field of 4 bits. Let's see. Yes, it's 4 bits. So we need to be a little bit careful here, because when we are dealing with 8-bit fields or 16-bit fields or 32 and so on, we can just list them from top to bottom. But it's a little bit tricky with those small fields, these 4-bit fields like these 2, because then we need to switch them. And that has to do with how these numbers are stored in memory. So this comes first and then this. So what we do is we say that this is an int8 IHL of 4 bits. So we define it like this. And we need to make sure that it's not getting padded by the compiler. So we need to define an attribute. So let's call this packed. And it's going to be an attribute like this, I think. Maybe just, I never seem to remember this, but let's say it's like this. Then we say packed, and make sure to make double parentheses. And we need to define this down here for the whole thing. And we also need to define it for each single one of them. Maybe we need to put it after. So so E packed, just like this. All right, and then we have the version field, like this. And then we have this DSP field, which also has only 1, 2, 3, 4, 5, 6 bits, which means that these need to be swapped. And how do we know which ones need to be swapped? Well, we make a group out of 8 bits, and those we swap. And here we have 8 bits, and we swap. So we first begin with this 2-bit ECN. And then we take this 6-bit DSCP. So it's a little bit tricky, but that's all there is. And then we have a regular 16-bit field, so we can just put it right as it is. And this is the length. And then we just carry on doing the same thing. And this options field we can skip. So we go all the way here. And when we have done that, we move on to the next protocol in the stack, which is UDP. So UDP packet wiki. And this is a rather simple protocol, not many fields. All we have is a source port of 16, destination port, length, and checksum, all of them 16 bits. And the data field, every packet level contains a data field, but here we put the next protocol. So we don't have to worry about data since we are making this struct from top to bottom. And finally, when we have done this, we go to DNS packet wiki. Let's see if we can get some. Here it is. Right. Yeah, we do the same thing here. We need to be careful with these because these have small bit lengths. But otherwise, we just carry on. So I'm gonna do this now, and I'm gonna pause if I find something which we need to think more careful about. Otherwise, I will just carry on finishing this thing. So see you just in a bit. All right, welcome back, you guys. So now we have this huge struct with all the different fields right here. So, and I made a little special thing here because by the end of this DNS packet, we have these number of questions, number of answers, number of authority RRs, and additional RRs. So all this starts with number of. So I made a substruct here, which I called num, and then I just called them questions, answers, auth, and so on, just to make the variable names a little bit shorter. And make sure to make all packed. So now we have D for DNS, we have U for UDP, I for IP, and E for Ethernet. And we just need to fill in all of these different fields in order to be able to send one of these things. So let's create a typedef for this thing. So typedef struct s packet, and let's call it packet like so. All right. So let's see here. So we need to create some kind of constructor function for this. Or do we now? Let's see. Maybe not, because it will be, if we create a function which takes all of these as arguments, it will be very difficult. But most of these fields will always be the same when we send packets. So maybe we should create a constructor function for it. So let's say we have our constructors. So this is going to return a pointer to a packet, and this is make packet. So what do we need for arguments here? Well, it depends. We need to fill in some of these. So let's not define the arguments right now. Instead, let's just fill in all of these, as many as we can, without having to care too much about what it needs to be, since most of these will be the same when we send this type of packet. So let's create this constructor function, which returns a pointer to a packet. Make packet, and I'm gonna do it like this. I want to allocate this on the heap. So let's say we have a pointer like this, and then I want to have something like this. Let's say we have the actual packet, and we don't make this a pointer, and then we define the packet by doing like this. So we say that this is a packet, and then we can define each part of this thing like this. So we can, for instance, say that first we have Ethernet, and then we have the destination, which is equal to something. And I guess we need to cast this like so. And then we have the source. And we have the type, which is some value which we will define, but not right now. And then we go through each protocol and fill in all we can with default values. By the way, this should be like so. And when we have this thing, we are going to allocate for it. So we need to calculate the size. So let's say we have an int16 size. Size is equal to size of struct s packet. And then we allocate. So something like this. And let's call alloc, because I'm not sure what allocator I'm going to use. So let's say we do it like this, and we allocate the size, and we assert that we have a p, and then I want to zero out that p, and we don't have this zero function, so let's write that first. So let's say we have something like void 0, and we take an int 8 star, which is the destination, and we have an int 16 for the size. So this zero function will just zero out any data structure. So void 0 int 8 destination int 16 size. We need to have some counter n. We need to have some pointer p. Do a for loop where we set p to the destination. We set the counter to our size. And then we are going to loop as long as we have an n. At each iteration we minus the n and we plus the p. And we just set p equal to 0. And then we return. Easy peasy. Alright, so now that we have done this and allocated for the thing, we want to copy these default values to this. And I guess the easiest way is just to do p equal to packet. I think that should be enough nowadays. And now we can just change the things we want to change here, and by the end we just return p. Okay, so let's see here. We need to figure out what type value that we're going to use for our protocol, which is IP. So let's go back to the, let's see here. So Ethernet frame wiki. I think it's 0880 or ether type value of 800 is IPv4. Okay. So let's say that this is let's say type IPv4, just to make it a little bit neater, and then we can define that. To 0x0800 like this. And what about source and destination MAC addresses? Well, I want to not focus too much about that, so I'm going to use static values in this case. So I'm going to run ifconfig, and this is my network card, which means that this is my MAC address. But this is in a slightly different format, so we need to, let's see, we need to add something like this and remove those. Like so. So this is our source. And I hope it's in the correct order. I'm not sure if we should reverse it, but I don't think we should, so this is probably right. And what about the destination? Well, this needs to be our default gateway. So what we can do is we run run route dash n. Okay, I don't have, maybe I need to call sbin. So here is our routing table, and my default gateway is this right here. And how do we figure out the MAC address? Well, we can implement ARP, which is the correct way of doing it, but since this is never changing in my case, and probably not in your either, we can just call sbin arp dash a n. If you run Windows, you run arp dash a like this and not n. And I'm gonna make it simpler, and I'm gonna grep for this IP address, and here it is. I mean MAC address. No, IP address. So we need to format it the same way. Like so. And that's it. Now we have Ethernet done. Now we can go to IP, which is a little bit more involved. I shouldn't have closed down all of these tabs. So IP packet wiki, IPv4. Alright, so the version should be 4. That's easy enough. IHL, what is that? Internet header length. So IPv header is variable in size, blah, 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 blah. The minimum value for this field is 5. 20 bytes. Okay, so that's what we need, because we are counting how many 32-bit integers we have inside of this whole header. So we need 5 of those. So IHL is 5. Then we have the DSCP and the ECN. That is for priority. I think we can leave them 0. Yeah. So DSCP 0 and ECN 0. And then we have the total length. Is that including everything deeper down? Defines the entire packet size in bytes, including header and data. So it is 20 bytes, but we need to take into account the DNS packet size, which is 64, let's see. So here we have 32, 32, 32. So we have 96 bits. $12 bytes for the DNS header, but we also need to take into account the UDP header. UDP packet wiki. And if I remember correctly, it's 64 bits. $32.64. So so 8 bytes. So what do we have here? We have 12 plus 8. That's DNS and UDP. So that's 20. And then we have 20 for the IP header. So 40 total. And we are only counting from the IP and down. So we are not, above here is the Ethernet, but inside of here we only count down. And same when we come to the next level, we count down for the length field. So let's set this to 40. What else do we have? Identification. For uniquely identifying the group of fragments. Okay, we are not using any fragments. We are sending one whole packet. So this ID field can be 0. Did I call it ID or identification? ID. And flags, I don't think we need to do anything there. And fragment offset should also be 0, I think. Yes. Alright, so flags and offset is 0. Time to live, that we should set to the default of 250, I think. Protocol, here we need to define the UDP, because that's next in line. Unfortunately, we do have some types here. So this should be 17. Let's do like we did up here. And let's say we have a type UDP 17. So protocol is type UDP. So this far we have been able to set all of these to a default value. We don't have to take any arguments as of now. Then we have the headers checksum. This we need to calculate, but we need to do this as a last step. So we will set the checksum to 0 for now. And then we have the addresses. The source address, I think I'm going to hard code actually. So my IP address is this, but we need to convert this let's see. Well, let's do it like this. So the source is going to be this, but we need to convert this to the right format, and we can use, there is a function called inet address, so I think I'm going to use that in this case. Let's see if we need to define anything for that. So inet address, we need all of these. Right. We will probably need these anyway when you're going to send this thing. The packet, that is. All right. However, the destination we need to define, and we need to take this as an argument to this function. But let's set it to 0 for now, and let's mark it like this, so I know that this needs to be taken care of. And that's it for IP. And then we have UDP, which is kinda simple. So source and destination port is 53, and that defines that we are using DNS. So every protocol has its own ports. So source is 53, destination 53. The length in bytes of the UDP datagram, the header fields and the data field. All right, so this whole thing we know is well, it's 8 bytes, and DNS is 12, so we set this to 20. And we need to calculate the checksum, but this is the same as same principle as above. We set it to 0 for now, and then we change it when we need to calculate the thing. So this far we have only needed to change one thing from the default. And finally we have the DNS part. Maybe we need to do this. Okay, so transaction ID. I think we can define this ourselves. So since we are only going to send one single packet, we can probably set this to 0. Indicate, so QR. And by the way, I defined these as booleans, since they are each 1 bit big, but you might have made them int 8s. It doesn't really matter as long as we're consistent. Okay, so QR indicates if the message is a query or a reply. Well, this is a query, so let's set QR to false. And then we have the opcode. So this is going to indicate if it's a query. Which it is, so we can set this to 0 as well. AA, authoritative answer in a response indicates blah 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 blah. Well, this is not necessary for the query. TC truncated. Set this to false as well. RD recursion desired indicates if the client means a recursive query. And that basically means do we allow that this will be forwarded down the chain of DNS servers? And yes, we do. And then we have RA, recursion available in a response. But we are sending a query, so we don't have to worry about that. Z, reserved for future use, okay. Set this to false. AD, authentic data in a response. So we don't need to worry about that since we're sending a query. By the way, maybe we're going to use the same function for different types of, but we can focus on the query actually, because we are not going to create any replies. If we're creating a server down the line, we can do that, but not now. Checking disabled in a query indicates that non-verified data is acceptable in a response. I'm not really sure. Let's set this to true for now. R code, that's a response code, which means we don't need to worry about that. Number of questions. So we need to go into our num structure. So number of questions. That's one. We're sending one question. Number of answers. 0. Number of authority RRs. I wonder if that's only applicable for the response. But we need to specify what kind of information we're looking for. Authority RRs. I'm not really sure if it's supposed to be authority or not. We need to experiment a little bit here, I think. So let's set authority RRs. We set this to 1 and we set the other one to 0 for now. Additional RRs is 0. So a resource record is one specific type of information we're looking for. So for instance, we are looking for an address. So the type is A. So A is for an IPv4 address. These A's are for IPv6. MX is for mail servers. TXT is for additional textual information and so on. So you can get a lot of different information from this thing. So we need to add this size of this RR field right here to our other lengths. So this and this. And the length of this depends on how long the address is that we are trying to translate. So the type and the class are 4 bytes. So we can do this. We can add 4 bytes to both lengths. And then we just need to plus the length of the thing we are trying to resolve. Maybe we can do it something like this. So let's just say that we have an int 8. Let's call this the resource record. Let's make it like this. So we can define this at a later state. At least now we know what we need here. We need the destination IP address of the DNS server, and we need the thing we are trying to resolve. So let's say int 8 IP int 8 host. By the way, we don't need to specify the name of this thing. Not here. Alright. So let's say we have an int16 length. And the length is, let's say we have some count function which count the number of bytes in a string. So for the length here, we can take 44 plus the length. Same here. And here we can say the destination is the INET address of the IP. And when we allocate for this thing, we need to add the length as well. And we need some more things here because this is not all. Type in the class. I guess we also need this right here. So we need to add 4 and 2, so an additional 6, which we haven't accounted for. So 50 plus the length and 30 plus the length. And what about here? So here is the length, and then 2, 4, 8, 10. Something like this. So let's create a data type for the rest of this thing. So we can make a data type for this whole thing, but not the name. Since that is first, and since it's variable, we need to take that into account. So So let's create a struct, and let's call it the, let's do this. Instead of RR here, we call this the data. We could call this an RR. So we have the name here. But we can't define this. but we will put it there anyway later on. And then we have the type, so int16 type, class, TTL, and RD length. And possibly some R data, which we don't need to define the length for. Let's call this an RR like this. We need to create the count function. Which is just going to count the number of bytes of a string. So int16 count, int8 source. We need to have some counter. We need to have a pointer. Then we can create a for loop where we set p equal to the source, n equal to 0. Going to carry on as long as we have a p. At each iteration we are going to increase p and increase n. And then we can just return n. Something like this. Alright, so this thing is starting to take form. So, let's see here. Alright, so the next step is going to create this resource record and copy over the host into it. Fill in the fields of the resource record that we just created, this stuff. And then we just need to be able to send the packet and receive it back. But I think this would be all for today. I really hope you liked this episode and with that you want to subscribe, because it's going to be a cool project this. And thanks for watching. Thanks for today.